Hello, George Romanic here. Today we are going to talk about Dalton's law of partial pressures. Very applicable law to atmospheric sciences. This law says that for an ideal gas, pressure of a mixture is equal to the sum of the partial pressures of gases that are making that mixture. That means air is made out of nitrogen, oxygen, argon, a little bit of water vapor, helium, and so on. So the total pressure exerted on your skin by the air is made up of pressures caused by nitrogen, caused by oxygen, argon, and so on, in the proportion in which they constitute air, namely nitrogen 78%, oxygen 21%, argon around 1%, even below, water vapor even less, and so on. Now, you might say, well, this is very logical. How else could it be? Well, there are two things that deserve to be said when somebody brings that argument. First, this law is approximation, so you see your logic already failed. If you have gases compressed at very high pressure and temperatures, then the ideal gas law assumption doesn't hold, and this Dalton's law of partial pressures also doesn't hold. That means the total pressure is not necessarily simple sum of the partial pressures. But even more important than this, what I just said, that is basically consequence of measurements and investigation, is the following. This business of logic is very misleading. What we consider logic is something that comes out from our brains. But our brains, through the time of evolution, evolved to protect us from the harsh environment. Your logic is a consequence of you trying to survive, not being eaten by a lion or tiger or shark. So nobody has very good logic when it comes to some particularities of science, because our brains didn't evolve to be able to solve integrals in a second, to be able to see at the scale of molecules, very small particles, and so on. Every day you wake up and it seems that the sun is moving across the sky. And you would say, well, logically, therefore, sun is rotating around our planet. Of course, that's not true. People for centuries thought that sun is rotating around Earth because they relied on logic. They looked at the sun and said, but look, it's moving across the skies. Of course, later it was clear that Earth is rotating around the sun. But that came thanks to measurements and objective analysis of these measurements and the laws of physics. So this business of something is logical or not logical will lead you only that far, and that far is really not that much far in science. So you have to rely on mathematical rigor and experiments. Let us investigate Dalton's law of partial pressures more quantitatively. Let us say we have a gas made out of blue, red, as well as green atoms. Pressure exerted by this gas, let's say on this wall over here, or we don't have to have wall to begin with. At any rate, pressure exerted by this mixture of gases, P total, is equal pressure of gas 1, let's say that's blue gas, plus pressure of gas 2, let's say that's red gas, and plus pressure of green gas, let's say that's gas 3. Of course, we could generalize this to n different species of gases, and we would say that P total is equal sum when the number of species goes from 1 to n pi. And that is Dalton's law of partial pressures. Of course, we can write this as P1 plus P2 plus P3 plus P4 plus as many species as we have. So in words, of course, this law says that the total pressure exerted by the mixture of gases is equal to the sum of the partial pressures of the gases that are making the mixture. In this case, blue, red, and green. We can get even better understanding of this law if we go back to our ideal gas law and equation of state. You will kindly remember that equation of state reads PV equals N R star T, where P is pressure, V is volume, N is number of moles of a mixture of a gas in volume V, R star is universal gas constant, and T is temperature. Now, given that N is amount of something, N is equal Avogadro number. Each N has Avogadro number of particles, which is 6.02 times 10 to power 23 of something. But in our case, that something is mixture of gases. So here we are just counting how many moles of gas we have. Well, if we have three different types of atoms of gases in this mixture, of course we could say that N total is equal N of gas number 1 plus N of gas number 2 plus N of gas number 3. It's just counting things. We can always add things that we are counting. Therefore, we can write for atoms 1 that are blue in this gas over here, that pressure of atoms 1 times volume that they occupy is equal number of moles of atoms 1 times R star times T. Atoms 2, we said, are red in this mixture, so P2V equals N2 R star T. And green atoms are species number 3. So we have pressure of green atoms times the volume they occupied is the number of moles of green atoms times universal gas constant times temperature. We can add these three equations, and we will get that P1 plus P2 plus P3 times volume is equal N1 plus N2 plus N3 times R star T. Well, this is N total, which means that P total times V needs to be N total times R star times T. And this is how Dalton's law of partial pressures applies to equation of state. In atmospheric sciences, we use Dalton's law quite often, actually, and that is in relation to dry air and water vapor. Let us assume that blue dots represent atoms of dry air. That can be nitrogen, oxygen, argon, and so on. And a red one are water vapor. There is very small percentage of water vapor in air relative to other gases, but water vapor is extremely important. It's the most, in fact, important gas for weather. And that is because of all these gases, nitrogen, hydrogen, argon, helium, and so on, only water vapor exhibits phase transitions in the atmosphere. And that is responsible for either releasing or absorbing latent heat and basically playing one of the main contributions to weather. At any rate, in terms of Dalton's law of partial pressures, we can say that pressure of air is equal pressure of dry air plus water vapor pressure, and we use E, small e, for water vapor pressure. And this is application of Dalton's law of partial pressures to atmospheric sciences, and we use this a lot. Using this analogy here, we can also write equation of state for water vapor, and that would be that E times V is equal NV R star times T, where NV is number of moles of water vapor in this volume V. Or, as I said in my video on equation of state, we don't often use this form of the equations of state in atmospheric sciences. We use the form with density that I derived, and that form says that E, pressure of water vapor, is equal density of water vapor times gas constant for water vapor times temperature. And if you study atmospheric sciences and thermodynamics of the atmosphere, you have to know this equation, where rho V is density of water vapor and RV is gas constant for water vapor, and the value is equal 461.5 joules per kilogram per Kelvin. You will remember that gas constant for dry air was 287 point something joules per kilogram per Kelvin. Now, let us go back to this air that is perhaps in your room or my room. And we know that air is made up of nitrogen, and that is 78% of air around you and air that you breathe. Oxygen is 21%, and argon is generally less or about 1%. If pressure in your room is 1000 millibars, and that's reasonable, typical value of the pressure, then you can see from this whole business of Dalton's law of partial pressures that pressure of nitrogen exerted on your body is 780 millibars out of these 1000 millibars, because that's the percentage of nitrogen. Pressure exerted by oxygen on your body is consequently 210 millibars, because 21% is oxygen. And pressure of argon is only about 10 millibars or less, because argon only occupies 1% of all atoms in your room or less. So, very beautiful and interesting application of Dalton's law of partial pressures, so you get better understanding of what is squeezing your body in your room. There is another application of Dalton's law of partial pressures that can save your life. If you're scuba diving, you have to know that oxygen, O2 that we breathe, and it is essence for life, is actually toxic if you breathe it at a pressure above 1.4 bars. So, if pressure of oxygen is above 1.4 bars, that's not good. You will get oxygen poisoning. But when you are scuba diving, so here is the surface of the water, that is, let's call that 0 meters. As you are going down, the depth is increasing. So here you are minus 10 meters. As the depth is increasing, here is minus 20 meters. As the depth is increasing, as you are going down, pressure is increasing. And you have to know that in scuba diving with tanks, you breathe air at environmental pressure. That's very important. So the air that you breathe is adapted to the pressure in the ocean or a lake, wherever you are diving, at the depth at which you are. Well, at the surface, we have approximately 1 bar of pressure. I derived this explicitly in my video on hydrostatic equation. I hope you remember that. At minus 10 meters, it's 2 bars. At minus 20 meters, it's 3 bars. And so on. You get the point. But we saw just a few minutes ago that at the surface, partial pressure of oxygen is 0.21 bars. Therefore, it will double at minus 10 meters, so it will be 0.42 bars. And so on. If pressure of oxygen at Z equals 0 is 0.21 bars, at what depth pressure of oxygen is equal 1.4 bars? Because you have to know that depth and you have to be aware of it. If you reach that depth, you can get oxygen poisoning. Well, now this is very simple to calculate when we know all these dependencies. So we have that 0.21 bars is decrease of pressure per every 10 meters of depth. That means I will reach 1.4 bars, but minus 0.21. Why minus? Because this is important. You already start with 0.21 bar. So you're not starting from 0. You already started from 0.21. So to reach 1.4, you need basically 1.19. But I put it like this so it's more understandable for you. And that will be reached at some height Z. So Z is equal this, and that is 1.19 bars, times negative 10 meters, divided by 0.21 bars. So bar and bar cancels. And if you carry out this calculation, you will get negative 56.7 meters. So if you breathe regular air at the depth or below the depth of 57 meters approximately, you are susceptible to oxygen poisoning. And all this is thanks to Dalton's law of partial pressures and the physiology of our body that cannot tolerate oxygen at pressure higher than 1.4 bars. This was the Dalton's law of partial pressures, with few examples and particularly application to atmospheric sciences and the air that we breathe. Until next video, goodbye.